In this work, I implemented a deep learning model for estimating the state of charge (SOC) of a battery. The model architecture combines CNN, bidirectional STM, and an attention mechanism to improve prediction accuracy. Uh, Coming to the model architecture implementation, I started by defining a function to build the model. The input consists of sequence of lines with multiple features. And coming to the CNN feature extraction block, I implemented a CNN block using convolution one-dimensional layers to extract local temporal patterns such as voltage and current variations. Batch normalization is used to stabilize and speed up training. And then I stored this output as a residual connection which will be added later to preserve learned features. And coming to the deeper CNN, I created the number of filters to 256 to capture more complex patterns and added dropout to prevent overfitting. And then I added the residual connection back to the main path to improve gradient flow and model stability. And coming to the bi-LSTM layers, I implemented bidirectional LSTM layers to capture long-term dependencies in both forward and backward directions. This helps the model understand battery behavior over time. And I have used the attention mechanism. I implemented an attention mechanism to allow the model to focus on the most important time steps. Here the dense layer generates attention scores, and softmax it converts them into probabilities, and it multiplies the importance weights. It reduces sequence into a single vector. This improves prediction by prioritizing critical time steps. And coming to the dense layers, then I added fully connected layers to learn complex relationships before prediction. And finally, I used the linear activation function since SOC is a continuous value. And then I compiled the model using Adam optimizer and Huber laws, which is robust to outliners. And the training pipeline implementation, it includes a feature selection. I selected both raw sensor data and engineered features to improve model performance. And then I converted the data into sequences using a sliding window approach. Each input contains 30 time steps. And then I split the data into training and testing sets without shuffling to preserve temporal order. Coming to the model training, I trained the model using validation data and callbacks like early stopping. After training, I generated predictions on the test data set. And then, since the data was normalized, I converted predictions back to original scale using inverse scaling. And I evaluated the model using metrics like maximum absolute error and root mean square error. And finally, I stored predicted SOC values back into the dataset for visualization. In conclusion, I implemented a hybrid CNN bi-LSTM attention model that effectively captures both short-term patterns and long-term dependencies, resulting in accurate SOC estimation.